There will be a midterm review session today. Is this time good for everyone? No? It's the bad time? What time do people prefer in general? 5:30? 5:30 is better? Okay, let's take a vote. How many people want 4:30? Okay, not too many.
Is tomorrow a possibility?
Is tomorrow a possibility? Do you guys prefer it tomorrow?
Yes.
How many people prefer tomorrow? How many people prefer today? Looks like slightly more people prefer today, but let's do it today, and maybe we can have a separate one tomorrow. If my TAs, if you're nice to my TAs, and if they happen to hold another one, yes. Oh, can we videotape it? Yeah, we could videotape it. It won't be as nice as this one, but yeah, it can be videotaped. But you won't be able to ask your own questions in that case, right? Okay, so today there will be one. What time? Who prefers 4:30 again? For today. Okay, who prefers 5:30? So it looks like 4:30 is dominant. So let's start at 4:30, and you can certainly come in at 5:30. And you should come in at 5:30 to ask your questions. And prepare questions for the review session. Look at the previous exams. You have the homeworks, or conceptual questions as well. Actually, conceptual questions are probably more important because you have the solutions for the exams online. Right? Okay, and the room is here. And we'll have food as well. So you can eat and ask questions. I don't know which one's more important, but hopefully both. Okay, this is Porter Hall. Right? I haven't checked out the room, but hopefully we'll be able to fit. Homeworks. Your homework 6 is out, but as I said, I encourage you to do the homework for preparation on the exam, and quite a few of you have already started actually, which is good. You have a new lab assignment, which is due. We changed the due date because it so happened that we scheduled it on the same day as the Spring Carnival. So it's not anymore that way. It's April 23rd, which is the Monday after that. So you have some more time for this lab assignment. How was lab assignment 5? Good? People find it easy? Easier than Verilog. Well, I guess we'll see. Okay. So in lab assignment 6, in 5 you did caches, right? But you did not implement the memory system. You assumed a 50-cycle latency on a cache miss, right? Now we're going to implement a more realistic memory hierarchy. You're going to add an L2 cache. You're going to add DRAM, a memory controller model, MSHRs. Hopefully you know what MSHRs are. Miss status handling registers to enable multiple outstanding misses, right? And for extra credit, you can actually optimize your design and add prefetching. And I would very much encourage you to do that, especially if you find the assignment easy. You can now get an extra credit by adding a prefetcher to your design. Instead of being reactive about caching the blocks that the processor has already accessed, the idea in prefetching is to predict which block the processor is going to access and try to bring that block into the cache before the processor accesses it. And you'll have freedom to experiment with different prefetchers if you do the extra credit. Okay? Hopefully it'll be fun. Readings, this is the virtual memory that we're covering. We have started covering and we'll continue covering. And I do have the prizes for the last lab's winners, but they arrived this morning, so I didn't get a chance to unpack them. So we'll do that. We'll do that ceremony later on. Yes?
When will grades for homework 5, will they be up before the exam?
So probably grades will not be up, but the solutions are up. So you can actually check your solutions. Solutions are already up, right? We put them up. Okay. Okay, last lecture we covered Bloom filters, so you should know what they are. We covered a lot on memory request scheduling in DRAM. I will not go over these, and we also covered some other ways of handling interference in DRAM. The main thing we focused on, the main problem we focused on was inter-thread interference in DRAM, right? When multiple threads, multiple applications share main memory, what kind of interference happens in main memory, and how scheduling policies that are optimized for a single core or optimized for maximizing data throughput through the data bus in DRAM lead to unfairness in the service provided to different applications, and how we can prevent this by designing more intelligent scheduling policies that are aware of the different applications or different threads sharing the memory system. And we covered two major things: stall time fair memory scheduling, parallelism array batch scheduling. You should know these. Actually, one reading is a required reading, parallelism array batch scheduling paper. We also talked about briefly other approaches to handling the problem, right? If you partition the channels such that different applications do not access the same channel, you eliminated the interference problem, right? Of course, what is the downside in such an approach? Now, if an application is very bandwidth hungry, if it actually benefits from using both channels, now you're constraining that application to a single channel, right? Which means that you're reducing its performance potentially. We also covered the idea of core request throttling. If an application is very intensive and it's hogging the queues in the system, and that's why it's getting better performance because of a DRAM scheduling policy that prioritizes heavy applications, if you will, bandwidth-intensive applications, then you can throttle back that application. Some logic can say, application, stop requesting for a while, right? This core, stop requesting for a while. You could do that in hardware. Okay, and we also started virtual memory. We talked about the motivation. We talked about how address translation is done. We talked about page tables, page fault handling. Hopefully this was relatively review for you. And today we will cover more on virtual memory and finish it. And we'll cover some interesting interactions between virtual memory and caches. Did you guys cover that in 213? How does virtual memory interact with caches? Okay, so hopefully that'll be exciting. Okay, so we already know what is the idea of virtual memory. The purpose is to give the programmer the illusion of a large address space so that the programmer does not worry about managing memory or running out of memory. And we've talked about this. And it's a hardware-software cooperative mechanism. The basic structure is indirection, right? You have a virtual space that doesn't exist, that's divided into pages. And you have a physical space that exists, physical memory, that's divided into frames. A page is the same size as frame. And somebody magically maps these pages to physical frames. And that somebody is hardware and software together. And we talk about the concept of demand paging, such that hardware and software together manage disk as well as main memory. So if a page is not in physical memory, then the operating system and hardware together bring that page from the disk into main memory, right? This is what's called a page fault. And we talked about the things that happen when a page fault is incurred on an access, right? So you should know all of that. So a page table is the basic structure that enables all of this, right? It stores the mapping of these virtual pages to physical frames. And we'll see it does a lot of other things. So this is the translation process. A virtual address is divided into two things, if you will, which one is the virtual page number, and the other part is the page offset, which byte in the virtual page you're accessing. And the translation process translates this virtual page number to a physical frame number going through the page table. So I guess if we can do this exercise, right? If you have 8 kilobyte pages and your virtual address is how many bits? We said 32 bits. Yes. Thank you. And if you have 8 kilobyte pages, that means that 13 bits, and this is a byte addressable virtual address space, these 13 bits indicate which byte in page that you're accessing, right? This is also called page offset. Offset of the byte that you're accessing within the page. And just to make it look like we've scaled this, And 19 bits determine the virtual page number. And you take these 19 bits and index the page table. And the page table, I'll call this the page table. Page table gives you a physical frame number, assuming this page is in physical memory. So what does this mean? This means that your page table needs to have 2 to the 19 entries, right? One entry for each page. So you get the virtual page number, use this to index into the page table, which means that your page table needs to have 2 to the 19 entries. What is 2 to the 19? 512, 512K, right? Yeah. Yeah, 512K, exactly. So it needs to have 512K entries, right? So if each of your page table entry is, I don't know, let's say 4 bytes, that means you have 2 mega entries, if you will. 2 megabyte page table, right? With this. Is that true? Yes. So just to warm you up, this could be an issue later on, right? And you have a page table per process. So let's start thinking about where this page table should be stored. So in this case, I guess 2 to the 19 PTEs, 2 to the 21, 2 megabyte. If you have 1,000 processes, you can easily have a 2 gigabyte total page table size. And should this be in physical memory or should this be in virtual memory? Well, if it's in virtual memory, how are you going to access it? Right. So there's a problem here, and we'll get to that problem. OK, so what's in a page table entry? This is where we stopped. We were talking about some of the bits in the page table entry. Basically, when you get a virtual page number, you need to know whether that virtual page is actually present in physical memory. Right? So there's one bit that indicates whether or not that virtual page is present in physical memory, and this is called the valid bit. I guess more appropriately, you could call it the present bit. I don't know why people don't, but it's the valid bit. If this valid bit is set, then the page is in physical memory and the translation, other things here can be trusted. If this valid bit is not set, then you get, this means there's a page fault. Right? Page is not in physical memory, so operating system needs to bring that page, or hardware needs to bring that page into physical memory. There are other bits. We talked about the dirty bits. This basically indicates whether the page has been written to, and the purpose is to write back that page to the disk when you need to do a page replacement, right? Essentially, this means that this dirty bit means that your DRAM is a write-back cache, right? It's a cache. It's automatically managed, except it's not fully hardware managed, right? It's managed by the operating system too. There is a reference bit. This could be actually multiple bits, or this basically tells when was the last time this page was referenced by the process. Well, not exactly, right? That requires a counter, timestamp, if you will. This basically says, in the last time interval, this page was referenced by this process. And periodically, the operating system goes and clears these reference bits so that you know if this reference bit is set, this page was recently referenced. Okay? So when a page fault happens, then the operating system needs to decide which page in physical memory should be kicked out. Right? So how does it decide that? How does it decide which page should be kicked out? Well, it goes through the page table, or maybe some auxiliary structure that caches these bits. It figures out an entry that doesn't have the reference bit set. Does that make sense? That means that this page was not recently referenced. So the prediction is that if it was not recently referenced, it's not going to be referenced soon. That's a prediction that's employed by the operating system. And so let's kick out this page and bring in the new page that's not present in physical memory. So that's one page replacement algorithm. Again, it's very similar to cache replacement we talked about, right? DRAM is a cache for the disk. So you could imagine many different page replacement algorithms. This is one algorithm. Actually, it's called the clock algorithm. A lot of operating systems use it. Basically, what happens is there's a pointer into the page table to examine the next page to be kicked out. When you get a page fault, the operating system takes this pointer, indexes into the page table, and inquires, checks whether that reference bit is set. If that reference bit is set, it increments the pointer, checks the next entry in the page table. If that reference bit is set. I'm, of course, assuming that these are valid entries. If that reference bit is set, again, the operating system doesn't replace that page, moves the pointer to the next entry, and checks the reference bit of the next entry. Operating system does this until it finds a page with a reference bit not set. Right. If that reference bit is not set, then that page can be replaced from physical memory. Okay? This is one algorithm, and this is clock algorithm. It's used in many systems today.
How do you set the reference bit? When do you set the reference bit?
When do you set the reference bit? When you set the reference bit when a load or store instruction accesses the page. Okay?
So if they're all valid, that means at some point they were all accessed. So all the reference bits should be set.
Yeah, if all of the pages are accessed in the last interval, yeah, then all the reference bits will be set. But the operating system goes through at the end of an interval and clears those bits. Okay? There are many other ways of implementing this, but I'm giving you one way. And you can see a lot of overheads associated with this, right? Yes?
So the reference bit has to be managed by hardware?
So exactly, reference bit, that's a good question. Reference bit needs to be managed by hardware. The hardware, when there's a load instruction, somehow that reference bit needs to be set. And we will get back to some other issues related to this. Every time you do an address, every time you do a load, you go ahead and access memory once more. Right? Okay, we'll get to that. Okay, what else is in the page table entry? There are other, well, of course, you need to have the physical frame number, which is the mapping. Assuming the page is in physical memory, then this tells you which physical frame the page is mapped to in physical memory. So if valid bit is 1, this physical frame number is to be trusted. There are also other bits, protection and control bits, and we will talk about that soon. These bits are used to determine whether or not this operation is permissible on this page. Can this process access this page, and can it access it the way it's trying to access? Like maybe the process cannot write to the page. Right? Maybe page is not writable. Maybe the process cannot execute this page. Right? So there is protection. This is actually a separate function of virtual memory, and I would like you to distinguish between these two functions. There are two functions. One is translation, address translation. The second is protection, and we'll get to that. So this is address translation illustrated for you. This is what I showed here, and you can look at it when you're preparing for the exam. And this also gives you all of this information that I said just now. And this is a simplified version of the page table entry. So when you need to access the page table, there is also a page table base register, which we will get to also. OK. So this is the case when you get a page hit, no page fault. Basically, you have the virtual address. This is, let's call it the memory management unit. Memory management unit fetches page table entry from the page table in memory and translates the address the way we talked and sends the physical address to the L1 cache. And L1 cache sends the data word to the processor. Is this good? There's something wrong with it, though, right? which means whenever you're doing a load, whenever you're fetching an instruction, you need to do this translation and do more memory accesses to access the page table. Right? So it takes a long time. So we're going to fix that. And this is the case when a page fault happens. And you can read this also. We've talked about all of these before. Let's talk about protection before we talk about how to speed this up. Not every process is allowed to access every page. So you may want to distinguish between supervisor and user, right? If you want to access the operating system pages, that's critical to the system, right? You may not want any user to modify an operating system page and, hack your system, if you will. So the idea is to store access control information on a page basis in the process's page table to ensure that you have access control at a page basis. So doing this enforces access control at the same time as translation. So in a sense, while we're doing this translation, why don't we also check if that page is accessible? Because you're already doing this translation anyway. You're already checking at a page level whether that page is present and where it is. So we can add access control to it as well. So virtual memory system serves two functions as a result of this. First is address translation for illusion of large physical memory to the programmer. The second is access control, protection. So you can think of it this way, which means that the page table entry contains access control bits associated with the virtual page. Which means that your page, what are these access control bits? It could be these, right? It could be, can you read this page? Can you write to this page? Can you execute this page? And it really depends on the system. And I'll show you examples from x86. It's actually, in x86, it's either read or write, although they've added recently execute as well. So this can evolve over time, too. Yes?
You also need, whether it's user or kernel.
Yes, that's right. So there is more encoding here, and I will get to that. So this is a very simple version. So what is access control? So I think this answers your question, hopefully. The processor is trying to do some access, so it has a type of access, right? And so I guess access control logic. It takes the access type from the processor. It could be read, write, execute, for example. It takes the privilege level of the process. It could be many things: user, supervisor. And if you look at VAX, for example, there are 4 levels: kernel, executive, supervisor, user, at different levels of privilege. User is the least privileged. They cannot touch all pages. Kernel is the most privileged. They're able to touch different pages, even the most critical pages. And there are also protection bits. These are the bits that I showed you in the PTE, page table entry. These bits basically specify, for this particular page, can this privilege level do this access type, right? Make this access. So on a per page basis, there is an encoding that specifies whether or not you can do an access type at this privilege level. Does that make sense? So if you have, let's say, 3 access types and 4 privilege levels, how many different combinations can you have? Any guesses? Say it again. 3 to the 4th, right? I think that's the right answer. 81. I'll let you think about that. Is that true? So you have 3 different access types and 4 different privilege levels, and a combination of these is really, you can have, 4 different privilege levels: kernel, user, supervisor. I think executive is the other one. User. And each of them can do 3 different access types. And for each page, you need to specify, can the kernel do read, write, execute? Can the executive do read, write, execute? Can the supervisor do read, write, execute? And there may be so many combinations, right? Yes. Huh? No.
It's kind of strange though, because it means that the kernel, for example, can't read, but the user can read.
So absolutely. So that was my next question. Do you need all of these different things? No, not necessarily, because it doesn't make sense for a lot of cases where like kernel doesn't have read access, for example, and user has write access. So you can actually prune the space such that the combinations are much less than 81. And in VAX, it was much less than 81. So you didn't need as many bits to specify this. Okay, yes.
So to think about it more, it actually might make sense to not let the kernel read, because like if you have copy and write, for example, your copy and write implementation might be written only such that it can handle faults from user mode. So if you have a fault from kernel mode, you might want to treat that as an error rather than something that's allowed, and force them to go through some routine to do a copy and write.
Okay. Yeah, maybe. Although it kind of doesn't make sense for the kernel not to have the privilege to revoke whatever the user does, right? Especially if it's the most privileged thing in the system. But yeah, let's take that offline now. I'd like to understand more. Yeah, there could be cases where different privilege levels make sense, where they don't make sense. Okay, but understand how this 3 to the 4th is calculated. I'll let you figure that out. You guys have taken probability courses, right? Or do you remember? Maybe. That's true. Well, combinatorics plus probability, or discrete math. You learn it in different classes. Okay. So these are basically this protection bit specify. This is in the PTE, remember? Well, let me not draw the PTE. These are the protection bits that tell you whether this page can be accessed with this access type at the privilege level that this process has. And the outcome is, this logic checks whether that can be done. The outcome is the access allowed or is it not? If it's allowed, then the translation, which proceeds in parallel, gives you the physical address, and that physical address can be accessed. If it's not allowed, now you get an access protection exception. And that's an exception, and the system needs to handle that. So what are these privilege levels? So this is in x86. x86 also has 4 different levels, at least in one particular way of doing the addressing. Operating system kernel has the highest level. There are other operating system services can be at different levels, and the applications, this is the user level, if you will. And these are the page level protections. So in x86 has different ways of doing things. So at the page level, they have only 2 levels, user versus supervisor, if you will. And the user is essentially this level 3, and supervisor is everything else. So ignore this page directory entry. Basically, each page table entry can have all these different combinations. User can have read-only access. User can have read-write access. Supervisor can have read-only access. Supervisor can have read-write access to the page. OK. So protection. Do we actually need virtual memory protection? Have you guys covered this in 213? You don't remember? It's been so long. I still remember the course I took, Introduction to Computing Systems. That was the best course, one of the best courses. OK, so no. The answer is no. Virtual memory is really not needed for protection. And actually, many systems didn't start out with protection. There are other ways of doing memory protection. I'll go over these relatively quickly. But they're not as elegant. That's the reason why they're not, well, they're used today, but they're not the best. Basically, there are 2 ways of doing protection. One is base and bound registers, and the other is segmentation. And they run into complexities as we need more protection capabilities, and we'll look at those. And virtual memory essentially integrates many different things. That's why I didn't put the rest here. We'll see what it integrates. So what are base and bound registers? Now we're assuming no virtual memory. You have physical memory. This is your physical memory. And you want to protect different processes from each other. One process shouldn't write to another process's space. How do you do that? Basically, you provide a base register and a bound register for each process. And each process uses a portion of the physical memory, right? Which means that everything belonging to a process must fit in that region. When a process is swapped in, the OS sets the base and bound registers. And when the process generates an effective address, if you will, it basically adds that effective address to the base and checks whether the resulting address is within the bound. Right. If it's within the bound, then it can access that particular space. Is this a good solution? Yeah.
You have so much physical memory, but you're only using a small portion.
That's right. Exactly, yeah. So basically, you need a large contiguous address, physical space for each process in this case. And your free space can be fragmented. And how do you actually do sharing of memory in this case, right? It's tough to do sharing. You could overlap the base and bounds, perhaps, and do the sharing, but it's not flexible. Right? So now you can see the benefit of this indirection that we introduced with virtual memory. Right? With virtual memory, you could do sharing easily. Two different processes can point to the same physical page with their with their page tables. Right? Okay, so that's one way of doing access control. The other way, which is a little bit better than base and bound, is having a segmented address space. And the idea is, for a process, you can have multiple segments, so you don't need to have this potentially contiguous address space. And your addresses divide like this. You have a segment number, and you have an effective address. And with the segment number, you index into a segment table, which gives you the base and bound. Now, you don't have a single base and bound per process, but you have base and bound for different pieces of a process's address space. Right? So you could have, for example, initially, machines start out with code and data segments, so that you cannot. This provides a level of protection within a process as well, right? If a process is accessing the data segment, it's not able to write to the code segment. Does that make sense? And you could now allow sharing of code segments between different processes. Two processes through the segment table, they have different segment tables, can map the same code to the same base, right, in the physical address space. So you could allow some sharing in this case. We're getting closer to virtual memory with segmentation. Although these are different concepts. You could actually mix and match segmentation and virtual memory. So basically, what is a segment? Effective address is divided into segment number and segment offset. And segment size is limited by the segment offset, the range of segment offsets, obviously. And segments can have different sizes because with this bound register. So now you have a segment translation, which maps the segment number to a corresponding base and bound. And you can have separate mapping for each process. Right? And you can do checks. Okay, are you actually within this bound? This is actually today, segmentation is used for another yes?
Is this where segfaults come from?
Yes, exactly. So when you get a segmentation fault, this is actually the reason. You get a segmentation fault. You're accessing an address that's beyond the segment's bound, if you will.
Doesn't it just say that even if it's actually a virtual memory thing? I'm pretty sure that they use the terminology in cases of it when it's
Yeah.
segmentation.
So x86, which is probably most of the computers you guys are working on today, has both segmentation and virtual memory at the same time. And we will not get into that. You can read the you can read the x86 manual. I don't know exactly what segmentation fault means when you get it in the operating system level, because the operating do you know?
Page fault for that address.
I guess everything is called segmentation fault, right? That's right. So you do not know whether it's because of the segmented addressing versus pages, right? Because you could operate x86 in both modes.
Unless it's 64-bit, which doesn't have segmentation, so you don't have to do the page faults.
Okay. Yeah, he knows about x86. You can ask him more. Yes, that's right. There are different modes in x86 where you can operate. But yeah, segmentation fault, to answer your question, I think more correctly, segmentation fault could be a page fault or a segment out of bounds fault, if you will. And probably you can discover it by going into the stack to figure it out. Because I don't think there is a page fault exception that's thrown, right? It's always segmentation fault when you exit. Okay, with that diversion, so what is the downside of segmentation? What is the downside of segmentation? Basically, the main issue is it creates a lot of fragmentation problems. A system may have plenty of unallocated memory locations. And again, you have to have this contiguous region, if you will, to map a segment. And segments can be of different sizes with these bounds, right? So just to give you one idea of another use of segmentation, you can use segmentation to extend an old ISA to support a large address space. So if you have, let's say, a small address space, let's assume that this is your physical address, like 16-bit address, you could use segmentation to get a larger physical address space. How? Basically, you take the segment number, some bits from the address space, and convert them into a larger base address, and that gives you a large physical address. Now you can have multiple processes going into different portions of a large physical memory without them having to specify a large physical address. Right? Does that make sense? Okay. So I've covered this relatively fast, but I'll let you think about it. These are different ways of providing protection and some level of translation as well. But they're not as elegant as virtual memory. Page-based virtual memory solves these issues. It ensures that the address space is divided into fixed-size pages, if you will. And it ensures that a virtual address space of each process is contiguous. Right? Each process is a very contiguous virtual address space, separately from any other process. And the key is it uses this indirection to give each process that illusion of the contiguous address space, whereas everything else is fragmented in the physical address space, right? Does that make sense? That indirection is the key to enable that contiguous address space. Okay, and this is, you already know how the page-based address space does that translation. Okay? So I guess the key takeaways, this indirection enables you to have a contiguous address space. And also, this page-based translation enables you to have access control that's within that address space. Right. Okay. Any questions? Nothing. Okay, let's talk about some issues in detail in virtual memory. The first issue, how large is the page table? We've talked about this briefly, at least for this case, right, where you had a 32-bit address space, virtual address space, 8 kilobyte pages, and 32-bit page table entries. I guess this brings about the question, where do you store it? Do you store the page table in hardware? Do you store it in physical memory? Do you store it in virtual memory? Well, in hardware, you probably don't want to store a 2 megabyte page table, right? And this is 2 megabytes if your address space is 32 bits. What if your address space is much larger, 48 bits? 32 bits is only 4 gigabytes, right? Which is not a lot by today's standards. If it's 48 bits, then you can do the calculation. And we will do a calculation to see how big these page tables can get. So can you store the page table in virtual memory? Well, no, right? Because you need to you need to do this translation, and if you're indexing a location that's in virtual memory, you still need to do the translation. This needs to be somewhere in physical memory. Does that make sense? Which means that you need to have what is called a page table base register address, which is a physical address. So what really happens is this points to this page table base register. Actually, maybe I'll do this. This is your physical memory. And let's say your page table is stored here. This is your page table base register for this particular process. And when a process generates an address, a virtual page number, what happens is this page table base register is added to the virtual page number, and that's how you index. You generate a physical address into the page table entry address. So this is the address of the page table entry. That's physical. Make sense? So that's how you get the page table entry. Of course, there is an issue with it, which is if your page table is 2 megabytes, and again, if you have 1,000 processes, then you wasted 2 gigabytes of your physical memory on just storing the page tables, just doing translation. You're not even using that to store data. You're using that to store page table entries. So the question is, how can we store the page table efficiently without requiring physical memory that can store all page tables and all page table entries? And the idea is multi-level page tables. Basically, instead of having this, you have a page offset and virtual page number. Instead of having a large virtual page number and indexing the page table this way, why don't we do this? We still have the page offset, and you have multiple levels. First, translate this part, index into a page table that's stored in physical memory. Basically, let me call this the virtual page number high and virtual page number low here, or level 1 or level 2, as you wish. So you have the, and let me call this a page directory, if you will, page directory base register, which is a physical address. You take this and add to it virtual page number high, index into this, let's call it the page directory. It's essentially a higher level page table. And this page directory tells you the translation for this bigger portion of the address space. So it gives you the base of the page table that stores the rest. So this is the page table base register, if you will, for this larger page. And what happens is you take this base register and add to it this lower part of the virtual page number and get to the page table entry for this entire page. Does that make sense? You guys are familiar with this, right? Multi-level page tables? Yes? No? Okay. So what does this mean? This means that none of this needs to be in physical memory, right? The only thing that needs to be in physical memory is this page directory, if you will. How to find out the second level page tables. Because each entry in the page directory tells you the starting address of the page table. And that starting address doesn't need to be in physical memory. You could bring it into physical memory if you get a page fault here. You could page in the second level of the page table. The only thing that needs to be in physical memory is something that tells you whether or not that page table in physical memory or in virtual memory. Make sense? So you've already seen this, so I'm going fast, but that's the key idea. Which means that now you need to store only a small portion of the entire page table, if you will, the page directory in physical memory. Okay. So page table size, if you do the calculation with a 64-bit address space, well, what do you need? You need 2 to the 52 entries in a page table. And let's assume that each page table entry is 4 bytes. You need to store all of this for a single process. And that's just one process. Let's say 1,000 processes. You multiply this by 1,000. I don't know if maybe you guys can do this calculation, but that's a big number. And that's the reason we have multi-level page tables, so that we do not store the entire page table in physical memory, and we require storing only the first level. So this is to give you how x86 does it. Essentially, I told you this is the directory, right? The top bits of the virtual address are used to index into the page directory, and this is the base register for the page directory, and it's the physical address. And page directory entry tells you whether the page table is actually in physical memory or virtual or not. And if it is, then that page table's base address, which is provided by the page directory, is added to part of the virtual address, the second level, to get the page table entry. And the page table entry essentially tells you the translation, and you concatenate that with the offset to get the physical address. Does that make sense? Okay. So how do you access the page table? I already told you, which is you take the page table base register, add to it the virtual page number. And there's another level of indirection in this case, in a multi-level page table. You could have some processors have page table limit registers. This basically tells you how much virtual memory you have allocated. Right? How big is your page table? And on an access to a page table, the processor can check whether you exceed the limit register. Right? If the virtual page number is out of bounds, which means that it exceeds the page table limit register, then the process did not allocate the virtual page, so you can have an access control exception that way also. Not all processors have this. And page table base register, which is the physical address that you need to access the page table to do the translation, needs to be part of the context of a process. Right? When a process switched in, this needs to be in the processor so that you can do the translation. In this case, I tell you page table base register, but in a multi-level system, PDBR, page directory base register, needs to be part of the context. Now you know what a context is. We already covered this. Program counter, processor status register, general purpose registers are all part of the context. And now we're adding one more thing, which is the page table base register, or page directory base register in a multi-level paging system. It's called CRT, Control Register 3 in x86. So some of the figures that I'll show you will have CR3. So this is, if you have a 32-bit virtual address, this is how things are divided in x86 with 4 kilobyte pages. So you take CR3, page directory base register, add to it the top 10 bits of the virtual address, get to the page directory entry, and assuming that that page table pointed to by that directory entry is in physical memory, you take that base register, this is the PTBR as I called it here, and add to it, I guess this is the middle 10 bits of the virtual address, get the page table entry, and this tells you the translation. This tells you the physical frame number here. Okay? Well, you can have multiple page sizes. We briefly talked about that. In x86, if you have a large page, 4 megabyte page, in a 32-bit virtual address space, you don't really need multi-level page tables because it's a huge page. So this is how they do the translation. You have the same page directory, except one bit tells you whether the page is 4 kilobytes or 4 megabytes. That's the PS bit, and I don't remember what it stands for. But if the PS bit is 1, then you don't go to the next level of translation, if you will. You just directly compute. This PDE specifies what is the physical frame number, where the frame is huge, 4 megabytes. Does that make sense? OK. And you can read this on your own. But what I would like to point out here is, if you look at a page directory entry, what you have is the address of the page table, the next level, right? Well, let's start with this. This is the CR3, control register 3. You have the physical address of the page directory. And if you have a page directory entry, 1 means this is valid, which means that the page table is actually in physical memory. Then you can get the address of the page table in physical memory. 0 means it's not valid, which means that the page table that you're trying to access is not in physical memory. Then an exception happens, and you need to bring in the page table into the physical memory. That's why they say ignored, and there are some actions that happen. Now the next level, this is the page table entry in x86. This is if the page table entry is valid, then the translation, then the page is in physical memory. And this is the address of the 4 kilobyte page frame, if you will. That's the physical frame number. And if the page table entry is not valid, again, you get a page fault. Right. OK? And somebody needs to bring that page in. So there are other bits in the PT and PDE, and you can have fun looking at the x86 manual, but it's no different from the fundamentals that I showed you. Let's go through some of the interesting ones here. Present bit. Actually, present makes more sense than valid, right? So present means it's in physical memory. That's the valid bit. I guess these are the privileged bits. Read-write. Can you do read-write? Do you need to have user or supervisor level access? Ignore some of these things. You could have actually write-through pages in x86. This is the access bit. This is the reference bit that we looked into in the generic page table entry. This is the dirty bit, modified bit. And this is the physical frame number. So this is an example from a real system in x86. And page directory entry is also similar, and they have privilege levels at the directory level as well. So you can look at it. So actually, things are even more complicated because we don't have a 32-bit virtual address space anymore, right? Because you want a bigger virtual address space. And this is the extended address space in x86, which is you have a 48-bit virtual address. And again, if you have only 2 levels, your page table, now your page directory becomes huge, right? And you don't want to store it in physical memory. So what's the solution? Well, add more levels. Right. And this is the 4-level paging in x86. CR3, in this mode, specifies the base register of this thing that I cannot even read, which is essentially the highest level of the multi-level page table, if you will. And then that gives you the base address of this next level. And that gives you the base address of what used to be the page directory. And that gives you the base address of the page table. And now you can do the translation after doing this 4-level walk. And if you want to extend your address space to 64, you add 1 more level, perhaps, right, in the future. Does that make sense? So the principle, we don't want to store a large page table in physical memory. So let's do the translation in multiple levels such that we can store only the highest level in physical memory, and everything else can be paged in through the usual virtual memory system. And I guess you can read this. This is just, I thought this was interesting. So there are different modes in x86. This is the long address mode, if you will. It's called IA32E. So you could address 4 petabytes of memory with, I guess, 52 bits. So they take the 48 bits and translate it to a 52-bit physical address. So this is like the segmentation we talked about. You could extend the physical address. You could have a smaller virtual address, but a larger physical address. That way you can have addressability in physical memory to 4 petabytes. Right? Of course, this is not for a single process because single process can address only 48 bits. That's what they're trying to say here. So at most 256 terabytes of physical memory can be accessed by the process. And you can have still 4 petabytes physical memory, and other processes can be accessing it. Yes?
What is the point of having a smaller virtual address?
So what is the point of? Because you may be bound by your ISA, right? You may want to have a larger physical address space, but
Smaller virtual address space than the physical address space.
yeah. So let's say you specified your ISA and your virtual address is 16 bits, but now you want to have a much larger physical memory. So ideally, you don't want to do that, but because of specification reasons.
They just extended it to 48 bits, so
Mhm.
they extended it more.
That's right. But then, again, you run into trade-offs, right? What if you extend the virtual address to a larger number that affects a lot of things in your processor, right? Now, your address needs to be computed with larger registers. You need to have larger buses, if you will.
Didn't they already change the ISA when they switched from 32 to 64?
That's right, yes. Okay, so let's take another issue in virtual memory. Any questions on this, on multi-level page tables? Okay. How fast is the address translation? Well, okay, let's start with this example, if you will. You get a virtual address, and you need to figure out where it's located in physical memory. The first thing you do is take the virtual address, add to it, take the virtual page number, the top parts of the virtual page number. Let's call this the virtual page number very high. Add to it this physical address, access physical memory, and get the base register of the next level page table. Add to it these 9 bits, and get the base register access memory again. Get the base register of the next level page table. Add to it these 9 bits. Well, these 9 bits. And get the base register access memory at that location. Get the base register of the page table. Add to it these 9 bits. Form an address and access memory. Now you get the page table entry. Right? So you've done how many memory accesses? 1, 2, 3, 4 memory accesses to actually do a single memory access. Right. Yes?
So basically, in a physical address space, one of the things, at least one of the things that stores this page directory will always be unreplaceable.
Will always be unreplaceable. No, basically this first level, the highest level page table has to be in physical memory. Yes. So to be able to translate an address, you're fetching an instruction. You got a virtual address. Now you need to do 4 memory accesses. Well, this is probably not a good idea, right? How can we make it fast? Well, the idea is we have these translations that do not change much anyway. So why don't we cache them in hardware, such that when we get a virtual address, we consult this cache of page table entries, and do the translation and access control really fast in one cycle. And that's the idea of a translation look-aside buffer. A translation look-aside buffer is indexed. It's a hardware structure that essentially caches page table entries. And it is organized just like a cache of page table entries. And you index, well, I will not call it index. You access it with the virtual page number, which means that you have an index from the virtual page number, and you do a tag match as well. And if the virtual page numbers, the page table entry corresponding to this virtual page number is cached in the translation look-aside buffer, now you have the translation, right? Does that make sense? Okay, you've seen the translation look-aside buffers before, right, in 213. That's the idea. It's essentially a cache of page table entries. That's nothing more than that. And the idea is to speed up the translation. If you can access that in one cycle, then you don't need to do 4 memory accesses. Okay. So, which means that since it's a cache of page table entries, when you access it, when you generate a virtual page number, you can get a hit or miss. If you get a hit, well, if you get a hit, what you have is you'll have the translated address. You have the physical frame number, let's say physical frame number corresponding to this entry. You use that and concatenate with it the page offset. And if you get a hit, then you'll get the translated address. Yes?
So even if you have like a four-way virtual memory structure, you still use all those virtual bits to access the transition lookup number, right?
You'll still, yes, that's right. That's right. So that's right. It's not multi-level. Translation look-aside buffer, basically, with translation look-aside buffer, what you cache is really this, the page table entry, for the entire page address. This is your real virtual page number, right? So you basically take this huge virtual page number, index, access the translation look-aside buffer just like a cache, and in the end you get the page table entry. And the page table entry may be there if it's a cache hit. If it's not there, then it's a cache miss, TLB miss, right? Well, what do you do on a TLB miss now, right? If it's a TLB miss, now you need to do this page walk, if you will. Because you don't have the translation, now you go through this to get the page table entry for that particular virtual page number. And you get the page table entry, then you would probably like to put it into TLB, which means that you need to replace some other page table entry from the TLB, because it's like a cache. So you could have replacement policies within the TLB. So what TLB entry to replace? You could use different cache replacement policies, LRU, for example. And who handles the TLB miss is another question, hardware versus software. Different systems handle it differently. x86 does it in hardware today, and we'll get back to this soon. But other systems like MIPS handle the TLB miss in software, and there are advantages and disadvantages to each. The other question is, actually, let me go to this. So this is the TLB. You can look at this. This is essentially a cache. But I would like to go to this one. Yes. So what happens in an address translation with a TLB? You get an effective address or virtual address. You do a TLB lookup in one or reasonably small number of cycles. If you get a hit, then you also do the protection check, because TLB stores the protection bits as well, right? Let's assume that your protection level, you can access it. Then you get the translated address in one cycle or a small number of cycles. Now you can have a TLB miss, which means that you need to do the page table walk to determine your page table entry, right? And page table walk is this walk, if you will. Figure out where your page table entry is, where that address's page table entry is. And at the end of the page table walk, you may figure out that the page table entry, the physical frame, the virtual page can be present in physical memory or not. If it is present, then this is not a page fault, so you update the TLB. If it is not present, then that's a page fault, right? Now you need to replace some physical frame in physical memory and bring in the page that you're trying to access into physical memory. And this is handled by the operating system in most cases. Yes?
How come there is no protection check if you do a page table walk?
Well, yeah, there needs to be protection check also. It's just not added here. Okay? Well, actually, it's here. It's here. It's in the end, you take this path, right? Yeah, you update the TLB if it's a hit, and you do the protection check, and then you do the okay. So after that page fault handling, you also update the TLB, and then you do the protection check. And if protection fault happens, then you need to take an exception. So you could get a TLB miss or hit, and you could get a page table miss or hit. A TLB miss doesn't mean a page fault, right? Okay, so that's important to know. Say it again?
I mean, you could get a TLB hit and then get a page fault at the end of that.
That's right. You could potentially. When would that happen? That means that your TLB somehow needs to be invalidated. So that means that you have a valid entry in the cache here, but this bit in the TLB says it's not in physical memory. Right? That's right. So you could get a TLB hit, but it could be a page fault that you need to handle. And that speeds up your page fault handling a little bit, if you will. But you're going to spend a long time anyway. OK, so what should be done on a page fault? What virtual page to replace from physical memory? We've talked about this with the reference bit, right? You could use an LRU. Again, we talked about in the previous lecture, but then that's very complicated for that number of pages. OK, let's take a look at TLB mishandling. Should the hardware handle TLB misses, or should the software handle TLB misses? And their advantages and disadvantages. Looks like I should plug in my computer. No. There it is. Seems like this should be the kind of signal that should really pop up during the presentation, and not everything else that shouldn't pop up. OK, if you have a hardware-managed TLB, well, if you have a software-managed TLB, what happens on a TLB miss? Basically, an exception is raised when you get a TLB miss, and the software, the operating system, needs to fill the TLB, which means that you need to flush the pipeline. You need to handle the exception, right? So that leads to a higher performance cost because you flush the pipeline, as well as the software now needs to figure out how to manage the TLB. So this is costly. The advantage of it is now the operating system can define the page table organization. You're really not tied to the specification that's provided in the ISA, if you will. ISA only specifies a TLB organization, right? And you can get a more advanced replacement policy. So you can think about how to do these things. I'll not go into this in detail. Whereas if you have a hardware-managed TLB, this is faster, right? There's no exception. The instruction that got a TLB miss simply stalls. And as you know, other independent instructions can be executed, right? If there are instructions that are not TLB misses or independent, they can be executed. But now your page table organization is pretty much etched in stone, right? Because hardware needs to handle that TLB miss. OK. Have you guys covered this before in 213? OK, I'll let you think about this a little bit. But let's take a look at some other issues. How do we do the address translation? In particular, do we do it before or after accessing the L1 cache? And this is another important question, right? We've sped up the translation quite a bit. But how does our cache get organized? So this determines what happens in the cache also. Is the cache actually virtually addressed or physically addressed? And we call a cache that's virtually addressed a virtual cache. A physically addressed cache is a physical cache. And are there any issues with a virtually addressed cache? And one issue we will cover very soon is called the synonym problem, or the aliasing problem. This is a problem when two different virtual addresses can map to the same physical address. Right. Which means that if you have a virtual cache, virtually addressed cache, same physical address can be present in multiple locations in the cache, right? Because you're addressing the cache using a virtual address, and different virtual addresses can map to the same physical address, which means that these two different virtual addresses go to different locations in the cache, but they may be actually referring to the same data. Now you could have a consistency problem if one of those virtual addresses is used to update that data. Right? The other virtual address is not aware of this. The other location is not aware of this. So you could have the same physical address stored in different locations in the cache, but one of them has different data than the other one. Yes? That's an excellent question, and we'll get to that. Actually, maybe, yes. Actually, let's get to that quickly. There are actually two issues related to caches, which one of them is easy to solve. first one is the homonym problem, as it's called. Same virtual address can map to two different physical addresses. How does this happen? Well, how does this happen? Or how can this happen?
Well, if you have multiple processes.
Exactly.
Between them.
Yes, exactly. If you have multiple processes, same virtual address, they have no relationship to each other between one process and the other one. So they could be mapped to different processes. And if you have a multi-threaded processor, let's say, that's running multiple processes, the same virtual address can be accessed at the same time by the two different processes, right? And they could map to two different physical addresses. So that's the reason why you have this problem. The solution to this problem is relatively easy. You could tag each virtual address, if you will, or each cache line with the process ID, right? Or address space ID, as people have called it. That way you don't run into that problem, right? Synonym problem is a little bit harder to solve. Different virtual addresses can map to the same physical address, and you asked why? Well, there are multiple reasons, right? Different pages can share the same physical frame, right? So if you're sharing two pages between different processes, like process 1, process 2, they could share the same page, right? And they could have actually virtual address 10 and virtual address 1,000,000, if you will, pointing to the same page. Even within a process, you could have, there are other reasons. You could have shared libraries, shared data. Even within a process, you could have copy on write pages, right? You could have different virtual addresses within a process mapping to the same physical frame, if you will. Okay.
Wouldn't it be read-only? If they were copying
That's right, yes.
read-only, so you wouldn't be able to write to them, so they wouldn't be.
That's right, but they will still be stored in different locations in the cache, right?
Yeah.
So when someone writes to them, something needs to happen, and those locations should not be cached, perhaps, the way they're cached.
You'll get
Yes.
a page fault.
You could, that's right, yes.
Doesn't the tagging solve the problem in the synonym case as well? Because if you tag the process ID and different virtual addresses map to different physical addresses.
No, right?
You're supposed to have the same data, but if one writes to it, like,
Yeah,
that's not.
that's right. Because the data is the same, but it's stored in different locations, right? If one process writes to the data, then you need to update that data or invalidate the other location. Okay, so do these create problems when we have a cache? Well, this really depends on whether the cache virtually or physically addressed. And there are different ways of organizing the cache. This is a physical cache. In this case, you do the translation first, and all of the addresses in the cache are physical, which means that a location, a physical address, a physical block is only in one place in the cache, right? Because you're indexing your cache with a physical address anyway. There's no way to, the same location can be mapped to different locations in the cache. If your cache is virtual, you first do the cache access and then do the translation. Right? And we'll see another example here. So what is why would you ever want to do this, if you will? Well, the reason is speed, right? Here, in order to be able to get the data, you first need to go through the translation, which takes some number of cycles. Your TLB access takes at least one cycle. Right? And only after that you can access your cache. Here, your TLB access is off the critical path, if you will. You can generate an address and directly access your cache. There's no additional cycles spent on that. That's the motivation for having a virtual cache. And we will get to this hybrid, kind of, if you will, and as a solution. So this is a physically indexed, physically tagged cache. It's also called a physical cache. Basically, you have your virtual address. You go through your translation. Actually, maybe I will draw some of these. You first do the TLB access, and you get the physical address, and then you use that physical address to index into the cache and do the entire cache access. So let's see what we have here. You have the virtual address, you have the virtual page number. You do the TLB access first, and TLB gives you the physical frame number, and page offset doesn't change. And you take this, now we have a physical address. You take this physical address, interpret it in a different way. Well, how do you interpret it? Some bits are actually specify byte in block. Some bits specify the index into the cache. And some bits specify the tag. And you use the index to index into your tag and data arrays. And you take the physical tag, if you will, and check if the physical address, physical block, is actually present in the cache. Right. This is simple. This obviously doesn't lead to any homonym or synonym problems. You've already translated your address. The other option, the exact opposite, if you will, is you don't do translation at all. At least on the critical path of the cache access, you don't do it. Which is essentially this. You take your virtual address, and you have your virtual page number, if you will, here, but you don't do the translation. You interpret this address as a cache address. You have the byte and block, and you have the index, and you have the tag, and you access your cache directly. Right. Now the downside is the synonym problem, right? A physical address actually can be anywhere, in any location in the cache. In fact, I guess a physical address, a physical cache block, your cache could be full of the same physical cache block, right? Does that make sense? Because you have not restricted anything, meaning all of your virtual addresses, different virtual addresses, can map to the same physical address. So that's a problem, right? Meaning when you write to a virtual address, you'll need to invalidate everything else. So, but the upside of this organization is this is very fast. It's very fast cache access. So ideally, we would like to get the fast cache access with a virtual cache, fast access, because no translation before cache access. But leads to problems with synonyms. Ideally, we would like this without this, right? So it's always good to strive for the ideal. And there's an almost ideal solution, if you will, which is a virtually indexed physically tagged cache, or virtual physical cache. And the idea is you do the TLB access in parallel with the cache access. So you start the cache access before doing the translation, but then do something a little bit smart to ensure that your physical, one physical address is not present in multiple locations in the cache. And what is that smart thing? Let's see. So this is your virtual address. You start the TLB access, and at the same time, let's do this. That's your virtual page number. You interpret the same address as a cache address. And let's do this. There are some bits of your virtual address that do not change during the translation. Right? If you use those bits as your index, you know that your index will not change during the translation. Which means that if you have two virtual addresses mapping to the same physical address, well, let me give you let me give you the solution first, and then we'll look at why this works. You take these bits, index bits, from the part of the virtual address that does not change during the translation, index into the cache, get the tag, and tag is a physical tag. In particular, it's the physical frame number, which you get at the end of the TLB access, right? And you check whether the physical frame number matches. And if it matches, you get a hit. If it doesn't match, you get a miss. Now what happened here? Basically, if you have two virtual addresses that map to the same physical address, they'll produce the same physical frame number. Right? And you already use the index bits from the portion of the virtual address that doesn't change during the translation. So two virtual addresses that map to the same physical address map to the same location in the cache. You restricted your index bits. And you're also checking the physical address as your tag. Does that make sense? Yes?
Why would we be storing the physical frame number in the cache instead of like data values?
Oh, this is the tag. This is the tag store. Right. Data values are here. Data values correspond to this physical, this block. Okay? So your tag is essentially the physical frame number. Yes?
If you get a TLB mess, then don't you need to wait for the translation to
Yes, that's right. Yeah, and for this particular cache, a virtually indexed physically tagged cache, you do need to wait for the translation to happen. Yes?
So which bits actually don't change?
So that's an excellent question. Which bits don't change? Well, page offset, right? If your translation affects only it doesn't affect the page offset bits. So you have 4 kilobytes, right?
So should you be modding it to, rounding it to nearest page or nearest cache line size? Because if you round to nearest page, it's always 0 anyway. So you should round it to like 64 bytes then?
I didn't get it.
Like,
What are you rounding?
because if it's a page offset,
So this is your virtual address, right? If you have a page of 4 kilobytes, you have 12 bits here to specify that. And you're not doing anything with these 12 bits during the translation. So you could use any of these bits to index into your cache, and you guarantee that nothing will change. Right. Okay? Okay, so this is one way of solving the problem. But there are issues with it, right? What is the issue now? Now your cache size is limited, if you will. So what could your cache size be at most if you need to do this? If your index bits need to come from only the page offset. Let's say you have 64-byte cache blocks. You have 6 bits here. And how many bits do you have left for your index? 6 bits, right? Which means that you have 2 to the 6 sets in your cache. They should map to different sets, hopefully. Okay? Yes?
How is your page size determined? Is it a hardware property?
ISA, right? Your ISA tells you what's the page size.
So across different versions of an OS, the page size will be constant.
Yes, that's right. Mm-hmm. Yes.
So
Okay? Okay. So you got it, right?
It makes sense.
Okay.
So your cache blocks are like 64 bytes.
Exactly, yes.
Since you want to alternate, which means like go to
Exactly.
different sets.
Yes. Okay. So what if we don't want this? Like what if we actually want a larger L1 cache? So one thing you can do is actually you have a virtual page number. This is your virtual address. And you can use some bits. You can take some bits in the index from the virtual page number. Does that make sense? So now your cache size can become bigger, right? This is still your virtual address, but this is your cache indexing scheme, if you will. This is your block offset. So what we're doing is we're really interpreting the same bits in different ways. This is for the purpose of translation. You have 12 bits here. And let's say your cache size is 64 bytes. So you have 6 bits here. The cache block size is 64 bytes. And let's assume that your index bits are these. Now if you use this virtual index into your cache, and this is the translation that happens, you get a physical frame number. At the end, you compare whether this physical frame number is equal to this. But now you have a problem, right? Because some bits change during translation. Let's say you take 1 bit from the virtual page number when you're indexing into your cache. This 1 bit here, single bit. This bit could be 0 or 1, right? Which means that 2 virtual pages with the bottom bit 0 or 1 can map to the same physical page, but be in different locations in the cache, be in different indices in the cache. Does this make sense? Because you use this bit that changes during translation as part of your index. And you know exactly where they can be in the cache. So I think to understand this, let's take a look at one of the questions from 741, one of the midterms that we've done. We have time here. Yes. These are actually basic concepts. So let's go through this question. Do you guys have it with you? Okay, maybe I'll find it then. Do we have it on the website? Okay. So let's see. Past midterms. Oh, it's not on the website? Or okay, I think it's this one, right? Okay, it's this question. Let's go through this entire question. This integrates the concepts of caching and virtual memory. So before I move on to this question, so the basic idea is if you have a physical cache, then you need to do the translation before cache access, which takes time. You don't want that. It's good because a physical address is stored in only one location. It's bad. You need to do the translation first. If you have a fully virtual cache, then you don't need to do the translation for cache access at all. It's good, it's fast. It's bad. Now a physical address can be stored anywhere in the cache. Right? Now if you have a virtually indexed, physically tagged cache, you take part of, you use your virtual address to index into the cache. Right? Now, if you take some of the index bits from the virtual page number, that means a physical address can be stored in multiple locations in the cache. Right? And those multiple locations are really determined by how many bits you take from the virtual page number. Right? If you don't take any bits from the virtual page number, if you do not take any bits from the portion of the cache from the portion of the address that changes during translation, then you guarantee that a physical address is in only one location, right, in the cache. So ideally, you would like to do that, but then that restricts your cache size, right? So we would like to actually take bits from the index potentially, from the virtual page number to index into our cache. That increases our L1 cache size. But now multiple locations can be stored. A physical address can be stored in multiple locations in the cache. So how do you handle that problem? One way is to say, okay, we're not going to handle that problem. We're going to take index bits from the cache, and we're going to live with a small cache. Right? So your cache size is your page size times the associativity. You guys get how we got that? Your page size, this is your page size, times the associativity will be your cache size. But we don't want that also, potentially. So if we take index bits from here, from the virtual page number, now we know exactly which locations, when we get a virtual address, we know exactly which locations can contain the same physical address. And we know that it's either, if you take one bit here, it's either index that starts with 0 or index that starts with 1. Right? And when we write to one of those locations, we can check the other location, right, to see if that actually contains the same physical address. And that's what this question will be about, I think. Okay, let's see. Shall we go through this? This is hopefully going to be a good preparation for the exam too. So what does the question say? We have a byte addressable toy computer that has a physical address space of 512 bytes. The computer uses a simple one-level virtual memory system. The page table is always in physical memory. The page size specified as 8 bytes, and the virtual address space is 2 kilobytes. The first question, how many bits of each virtual address is the virtual page number? So we know that virtual address space is 2 kilobytes, right? 2 kilobytes means 11 bits. You have a virtual address that's 11 bits. And page size is 8 bytes, which means that you have 3 bits as your page offset. Which means that your virtual page number is 8 bits, right? That's the answer to the question. How many bits of each physical address is the physical frame number? Now we look at the physical address. Physical address space is 512 bytes, which means that you have 9 bits for your physical address. And we've already given you the page offset is 3 bits. So your physical frame number is 6 bits. Right? Okay, that's easy. It says we'd like to add, okay, you guys read that? We'd like to add a 128 byte write-through cache to enhance the performance of this computer. However, we would like the cache access and address translation to be performed simultaneously. Well, for the reasons we discussed. In other words, we would like to index our cache using a virtual address, but do the tag comparison using the physical addresses, virtually indexed, physically tagged. The cache we would like to add is direct mapped and has a block size of 2 bytes. The replacement policy is LRU. Answer the following questions. How many bits of a virtual address are used to determine which byte in a block is accessed? Well, that's easy, right? If you have a 2-byte block, you have 1 bit to determine which byte you're accessing. So this is your virtual address, and let's interpret this as you would access your cache. So you have a 2-byte block, which means that 1 bit for bytes in block. Right? I think so. Now the next question is, how many bits of a virtual address are used to index into the cache? Okay. So now we need to figure out what was this? 28 byte write-through cache. 128 bytes. Each block has 2 bytes, so you have 64 blocks, right? Is it a direct map cache? Okay, it's a direct map cache, so you need, I guess, 6 bits here, right? So this is your index into the cache, which is 6 bits. Make sense? And then how many bits of the virtual page number are used to index into the cache? Okay, now let's take a look at the virtual page number. So this is your virtual address. You interpret it as your index. So if you align these things here, you have 3 bits here, and you have 7 bits here, which means that these 4 bits that come from the virtual page number are used to index into the cache. Right? 2 bits come from the page offset. Okay? So 4 bits, which means that bits, I guess, if we look at the bits, bits 3 through 6 here. We'll use that later on. What is the size of the tag store in bits? Show your work. I guess you could calculate the tag store in bits, right? I will not go into that because that's the easy part. So let's look at the part B of the question. That's hopefully this will clarify some of the things we talked about today. This is part B. Okay, suppose we have two processes sharing our toy computer. These processes share some portion of the physical memory. Some of the virtual page physical frame mappings of each process are given below. You have process 0, those virtual to physical mappings. Process 1, virtual to physical mappings. And the question is, give a complete physical address whose data can exist in two different locations in the cache. Right. So how do you go about solving this problem? Basically, if you look at the two processes, you see that frame 3 is shared by the processes, right? In one process, it's at page 15. In the other process, page 15 is mapped to the frame 3. In the second process, page 7 is mapped to frame 3. Right? Which means that because we're using the index bits here, that is coming from the virtual page number, that frame can be present in two different locations, right? Basically, any byte in frame 3 is seen as two different virtual pages. So we could pick any byte. What is frame 3? Well, frame 3 is, I guess, what would be frame 3? You have 9 bits. So frame 3 is 1, 1, right? And 0, 0, 0, 0, right? Is that correct? So this is frame 3. And the question is asking for a complete physical address. So any byte, you can pick any byte within the frame. So this could be present in multiple different locations in the cache. And how many different locations? Well, it could be present in actually 16 different locations, right? Because you took 4 bits from the virtual address. Okay. Give the indices of those two different locations. So how do you do that? Well, in this case, page 15. So this is your physical address. And this physical address in process 0 is mapped to page 15, right? So what is page 15? Here, let's take a look. Your virtual address has 8 bits. So what is 15? 1, 1, 1, 1. That's 15. 0, 0, 0, 0. So 0, 0, 0. This is virtual address 1. That maps to that location. And virtual address 2 that maps to that location in process. Let me call this virtual address 0 because it's in process 0. And this virtual address 1. That's page 7. And it'll be 1, 1, 1, 0, 0, 0. Okay? So these two different virtual addresses are mapped to this physical address. And they happen to go to different indices. Why? Because you take bits 3 through 6 to index into your cache. So what are those bits 3 through 6? We chop off these bits. 1, 2, 3, 4. These are the 4 bits. Oh no. How many bits did we take? Yeah, 6 bits, right? Yeah, 6 bits to index into our... Oh, let's not chop off. So these are the 6 bits that you use to index into your cache, right? Because your cache block size was 1 bit. So this is index 0, if you will, and this is index 1. So the same physical address can be present in this index and also in this index. Different location in the cache, right? Okay? So that's that part of the question. And then the question is, we do not want the same physical address stored in two different locations in this cache. We can prevent this by increasing the associativity of our virtually indexed physically tagged cache. What is the minimum associativity required? I hope it doesn't sound cryptic by now. Well, what does this mean? This means that the reason these two locations were, the same location was present in different indices was because we took some bits from the virtual page number to index into the cache that could change in any way. Right? The operating system can map this virtual page to any physical frame, so that index could be anything for the same physical page, for the same physical address. So if we do not take the index, if you will, from the virtual page number, then we don't have that problem. We don't have the same address mapping to multiple locations, which means that we have 4 bits taken here, and we want to preserve the same cache size, right? That's right. So how do you do this? Basically, we want to eliminate 4 bits from our index, but we want to preserve the same cache size, which means that we need to increase our associativity of the cache. Right? So your associativity needs to be 2 to the 4, 16, because we start with direct mapped. Does that make sense? So you could actually look at the answers to this question also. So minimum associativity is 16, which means that now your cache access time could increase also, right? So now last question is, assume you would like to use a direct map cache. We don't want the 16-way, but we still do not want the same physical address stored in multiple locations. So how do you ensure that? Well, we didn't talk about how to do that. But there are other ways of doing this. Instead of just increasing the associativity, you can still take index bits from the portion that changes during translation, but do something else. Yes? Oh, but then you lose the benefit of virtual index physically tagged. Yes, that's a good try. We still want to keep it virtual index physically tagged. So, okay, there are 2 ways of doing this. One is called page coloring. Basically, the operating system ensures that these bits do not change during translation. Right? Now the burden is on the operating system. The operating system, if the virtual page number, these 4 bits of the virtual page number are always mapped to a physical frame that has the same 4 bits at the bottom. An operating system can do that, right? It knows the physical frame number, it knows the virtual page number, and it just ensures that a page that has these 4 bits are mapped to the same, a frame that has the same 4 bits. This idea is called page coloring. And it is used in Spark processors. Spark processors had a virtual index physically tagged cache, and this is how, in the operating system, they ensured that 2 locations, the same physical address does not get mapped to the different locations in the cache by doing this. Ensure that these bits do not change during translation. This is a software solution. There is also a hardware solution, which is costly, which is also implemented in processors. And the idea is, OK, let's live with the same address getting mapped to different locations in the cache. Well, I guess in this case, that wouldn't be answering the question, I guess. But the answer to this question is really page coloring. But another way of handling this problem, what is the downside of page coloring? It restricts the operating system, right? Now, the operating system can have a free page that happens to have the bottom 4 bits as 0, 0, 0, 1. But you're trying to allocate a page that happens to have bottom 4 bits 0, 0, 0, 0. But you cannot do that because they don't match, right? And you have to ensure that these things do not get mapped to different locations in the cache. So that restricts the operating system. So the hardware solution to the problem is ensure that the any page can get mapped to any physical frame. But now you know which indices the same address can be potentially stored. In this case, in 16 different potential places, right? So when you do a write to a location, to a physical address in the cache, you also check what other potential indices that address can be stored at and see if that location is actually stored at those indices. In a sense, you'll probe the cache 15 more times at the 15 other indices where this physical address could be stored at. And if the physical address happens to be stored at one of those locations, you either invalidate that or you update that as well. And you do this on a write. Does that make sense? And this was actually this. Let's go back to our slides. Yeah. This is the second solution over here. On a write, search all possible indices that can contain the same physical block and either update or invalidate if that physical block exists. And this is used in alpha 21 to 64 and MIPS are 10,000. I think in MIPS there were four potential places the same physical address can be stored in the cache. And when a store happened to the L1 cache, they checked all of those places and invalidated the location if it happened to store the same physical address. So I guess these are the solutions. These are the 3 possible solutions. If you have other solutions, you can certainly come up with some, perhaps. Everything clear on this? OK. It's an interesting problem with the cache virtual memory interaction. And the problem happens because we want to design processors as fast as possible, right? We don't want to wait until this translation to access the cache. And remember, caches, L1 cache is on the critical path. That's the reason. If you increase the access time by 1 or 2 cycles, you lose a lot of performance. And this problem, by the way, this problem is not present in higher level caches, if you will, because you will do the translation by the time you access your L2 cache. So it's only a problem at the L1 level, L1 cache level. OK. So in a similar vein, I will not go into this, but there is also a virtual memory DRAM interaction, right? We covered the virtual memory cache interaction. And that interaction happens because operating system can affect where things get mapped in the cache. And if your cache is virtual, partially virtual. Operating system also influences where an address gets mapped in DRAM. And we've seen that. And if it knows the structure of the DRAM, it can control which bank, channel, rank a virtual page is mapped to, right? So it could do things like this. It could perform page coloring. This is a different form of page coloring to minimize bank conflicts or to minimize inter-application interference, right? It could map different applications to different banks or channels or ranks. So I'll let you think about that. Actually, a similar thing can happen in caches also. The operating system influences which applications are mapped to which indices, if you will. Right? So if the assuming you have a cache that's shared between multiple threads, the operating system can partition that cache, if you will, by ensuring that the virtual pages of different applications or different threads get mapped to different indices. Right? I'll let you think about that. So I guess that's all. I'll see you at the review session later on today.